Thin lens versus thick lens. This is for your knowledge, but it's not. I'm not going to ask anything on this one either. So I may ask you about the thin lens formula, but not the thick lens. So essentially, you can do a simple maybe pinhole lens assumption, which we are also using in the multi-view geometry. Field of view. These are the things that I want you to know. Okay. So I want you to be able to compute field of view. Okay. Find the magnification if there is an object at a certain distance. What will be the magnification depending on the focal length and the distance? I want you to be able to do these simple math. This is not very important. Shutter speed. Okay. This slide, I want you to also know about this slide. Okay, how the light is proportional with the aperture area, the distance, the definition of f number. If you like to get the equivalent amount of light for different aperture sizes, the exposure time, and so on. So this slide is important. Understand this slide. Okay, and also this one right here. Those two slides. I also want you to understand the concept of circle of confusion. So understand this circle of confusion concept. This slide, okay, also study this slide. Okay. So how circle of confusion, this distance over here, is related with certain parameters in the optical system and so on. Okay, so also study this slide. By the way, the exam is going to be open notes. Okay, so you can bring your notes. I'm not going to allow any laptops or smartphones, so you can do a printout of all the slides. Okay, maybe in handout format, so that we don't have too many. So that and study these slides. And if you don't need to memorize it. All those things, or if you like to go to a specific slide, you know where it is, and you can go there and get the answer, derive the answer from that. Okay. These things are not critical. This is some general knowledge that I want you to know about. These different things, processes in the pipeline, they are not critical. Okay, you can just read about them, but I'm not going to ask anything on those. Filtering operation, you learned, you use filtering operation. Okay. So you can have cross correlation or you can have convolution in one of them. You flip the kernel. So these are some things that you should know. I may not ask anything about these things, but these are some of the things that you should know. And again, these are not very critical things. Okay. But as a general, knowledge on this area, it's a good idea to read about these and so on. Know the basic concepts. So I give you the critical, slides in the from the first lecture. Okay. Let's come to the second one, the edges, edge detection. So these are again some background information. What is gradient? How we calculate the gradient? This is something important, which you should know. Okay. From this, actually, we have discussed the solvable operators. Okay, and you already implemented in an exam, so you know how solvable operator works. The effect of noise, and we know that in order to get to know the effect of noise, first we need to apply some sort of Gaussian filter. So these are very simple things. So once you apply the Gaussian filter, and then you can apply a derivative filter, a solvable operator, for example, and look for the peaks, or you can get the second order derivative and look for the zero crossings. This is also something that you need to know. I may not ask a question, but this is something, as I said, important for this class. So the Laplacian of the Gaussian can be used for that purpose, and Laplacian of Gaussian this filter can be used in some other applications as well. So this is something that you need to know. Okay. So this is, for example, Laplacian of Gaussian operator for 2D. Okay, so you have the Gaussian filter, you have the derivative, okay, and this is the Laplacian operator, which is the derivative in the horizontal direction plus the derivative in the vertical direction. So when you find the Laplacian of Gaussian, you get something like this. And with this filter, once you get this filter applied to an image, your edges should be the zero crossings. So this is one way of thinking about it. Some approximations, they are not very critical. Okay. And the Kenny edge detector, we discussed the idea about the Kenny edge detector. I may not ask you a question on this, okay, but as a general knowledge in this area, you know, read the Kenny edge detector, how it works, and so on. Okay, so this is lecture 2. We didn't talk about Fourier transform. We talked about morphological image processing instead, which we brought from the future lectures. Okay, so this will also be part of the exam. So I want you to understand, you know, these set operations, you know, erosion, dilation, and being able to read that set operation. I may give you a set operation, okay, X such that this and this intersection, this is that, and so on. Something like this. Okay, I may give you a small object and then give you an operation. I may come up with something, okay, and say apply this operation on this object, for example. Okay, so you need to be able to read this and understand this and understand what this is doing. Okay, so for this you need to understand, you know, the dilation one, you know, the erosion one. These are the key ones that you need to understand, how you translate intersection, union, difference, and so on. So these concepts are important. So I may give you, as I said, some object and ask you to do some operations. There are complicated ones, such as, you know, iterative ones and so on. We're not going to go in such details. Okay, so they are not critical. Hitoriness, finding convex hull skeleton, thinning operation, pruning operations. I'm not going to ask any question on these specific things in the exam, but some very basic set operations could be part of it. These things, not critical. Okay, all these slides, you don't need to memorize any of these or even study these things. Now, there is application of these morphological operations to grayscale images. We skip that part. So this is not part of the exam. The grayscale ones, these final slides are not going to be in the exam. Okay, so all these after, let me see, extension to grayscale images. After this slide, including this one, nothing is going to be in the midterm exam. And then we discussed image enhancement. Here the critical thing is the histogram equalization. So this thing, essentially, this equation, given the histogram, normalized histogram of an image, how you can find the histogram equalizing function. If you apply that function, what's going to happen to your image? Okay, so this is something that is important. I'll ask a question on that. And also in the second problem set, there is a question on histogram equalization. We will talk about that. So definitely learn about the histogram equalization. Okay. Medium filtering, spatial filtering, these are things that are not critical. I'm not going to ask anything on that. But from this lecture, learn about the histogram equalization, how you can apply it when your signal is continuous, which is integral thing, and if you have a discrete signal image, how you will extend that idea to discrete images. So those are important. Okay. So that's the image enhancement. Half transform. This is also something important. This essentially, this part is understand how transform is critical. You know, going from the image space to half space. How you do that? The linear one, and also you can have the color representation of the lines. So learn about both of these. So these things are important, and as you will see in the second problem set, there is an example on this one as well. So learn about this. Okay, how to transform linear one as well as this color representation one. Okay, this part is not critical. Okay, so extensions, different versions of half transform. There are others, templates, circles, there are half transforms to take such things, parametric shapes. They are not going to be part of the exam, and we didn't cover. Okay. Linear algebra review, this was just a review. Okay, not important. But we use those things in the final part, which is the imaging geometry and camera calibration. Okay. These slides are, folks, important, especially in three-dimensional coordinate systems. How, for example, the coordinates are related with respect to each other. Okay, so there is a rotation matrix, and then there is a translation vector over there relating to coordinate systems. Understand this. Okay, and then you can, when you can represent these coordinates with respect to one another, you can also do the projection. Okay, project this three-dimensional point into a two-dimensional image plane. Okay, that is also important. How you do that? Using this function over there. Of course, we wrote it in homogeneous coordinates. Okay, and we wrote, also we incorporated the camera intrinsic parameters. Okay, so these are important. If I say there is a calibrated camera, then that means the intrinsic parameters are found and the pixels are multiplied with the inverse of that, so that you have a metric system. I'll give an example on that later on. So these parts, folks, are important. So understand, go over these slides and understand these things. Radial distortion correction, it's not critical. Okay, you may have issues in real life, and you can find the parameters that you apply and undistort your image. So we'll be assuming everything linear, and these nonlinear transformations are handled. So it's not going to be critical. Okay, these slides. This slide especially. Okay. And finally, intrinsic and extrinsic parameters. How we can find those things. This is also important. You have a calibration rig where you know X, Y, Z's. Okay. Doing this formulation, you have some steps. You can find RNT. You don't need to know the specifics of this QRD composition and so on, but you should know how this thing works. Planar case, instead of a three-dimensional target object, you can use planar ones, and there is all these mathematics in the other reference slides. You don't need to know the details of the mathematics for the planar case, but know the mathematics for this one. Okay, when you know X, Y, Z inward coordinate system. Okay, and how you relate it to the pixels and how you find those are important. Okay, this slide is important. Okay, when you have two views, how are coordinates x2, x1 are related? You should be able to understand this, and if necessary, do some manipulations on these. Okay. And in this problem, we have these measurements. We will try to find other things. What are the steps that we did? Okay. So from that, we got this essential matrix. The structure of the essential matrix is important. And if you have an equation like this, all the details are shown here and also in the reference slides. You don't need to know SVD, you don't need to know all the details, but you need to know the steps. We have this, for example, matrix, T times R matrix over there, okay? And you have all these parameters in there. How do you do these equations? You vectorize, you put all those unknowns in a vector, and then from there you use the SVD to solve for these. You need to know these steps, okay, these basic steps, but as I said, not the details of them. Okay. This is also something important. This part, for the planar case, the transformation becomes an homography. Okay. You need to know that this part is not critical. These derivations are not that critical. Okay. And these things, as I said, they are not very critical. And also finally, for the stereo, how we get these depth is important. When they are rectified, like when they become side by side, rotation is identity, it is just translation. For that situation, how you can find the depth of a point. Also, if there is rotation and translation, for that situation, how you can find the depth of a point. Okay, these are some important things that you need to know. Okay, and these slides, they are not critical. These slides that I put over there, you can read them, but they are not critical slides. Some examples are placed in the final, version that I uploaded. They are not critical. Fundamental matrix is when there is no, the calibration is not known. You have the fundamental matrix. You can look into the equation here. That also is not critical. Okay. So finding fundamental matrix and so on, all the slides shown here and also in the reference slides that we've covered. You can take a look, but they are not very critical. Okay. So after this, let's come and take a look at this problem set number 2. Okay. All right. I would like to maybe